how a CNC router works. It's probably a lot simpler than you think it is. It can be as convoluted as you want, but the actual mechanics of it, which is what we're gonna go over today, is pretty simple. I'm doing this video now because there's about to be a lot more CNC working in my videos. It's not gonna replace everything, but this is a tool I'm gonna use to achieve things I can't do and speed up some processes. So anyway, a CNC router fundamentally is just that. It's a router, but it's controlled by a computer. CNC stands for computer numerically controlled. So in here, we just have a 3 horsepower router, or a spindle is what we call it. This one's water cooled. They could be air cooled. Water cooled stays can run for longer times without worrying about overheating because we're pumping coolant through it. We've got a reservoir underneath. Whereas if it's air cooled like a regular router would be, overheating can become an issue. But ultimately, whatever bit you have down here is doing your cutting. Now normally when you are using a router manually, you don't use that to cut straight lines, but on the CNC, you can use this to cut, 3D contours, straight lines, curves, whatever you tell it to in the software. But if we're doing straight lines, we're probably gonna use a spiral bit, but we could also have a V bit to do V carves. There could be roundovers and chamfers. If you're doing 3D profiles, you'll probably get to some ball nose bits to do finishing passes, and we'll later do a video on like when you can use what bits, but ultimately here is where the wood cutting happens. The wood cutting is driven by the spindle, can be air cooled or water cooled, and these have a speed range just like your regular router does, where you just spin a knob, except on a spindle like this. This is actually a 3-phase spindle. I believe it's driven by a VFD that has a control panel here, and fortunately, in our machines, the software, we can actually set the speed, and so we don't have to worry about manually setting the speed. The software does that. We'll get there. And if it wasn't obvious, of course, here's my dust shroud. So this one opens up to make it easy to change the bits without taking it off. Normally, there'd be a dust hose here. That's your dust extraction. Obviously, though, in order to actually do any cutting, spinning is one thing, moving is the other thing. If it just sits in one spot, we don't have a wood cutting machine, we have a fire starting machine. So the Z-axis is the axis that goes up and down. This machine's actually conveniently labeled. We have an X here, tells you where the X-axis is this way. I have a sticker on this side for the Z-axis that helps you remember Z is up and down. And we have another sticker on the side of the gantry, Y-axis. And this even is dummy proof. Even has the plus and minus to let you know if you push plus on the controller, it's gonna go that way, minus is gonna go that way. Same thing with the X and the Z. And this whole upper assembly is called the gantry. This is the gantry, just like if you were in a metal shop or something, you might have a gantry crane. Same kind of thing, except a gantry crane would go across a building and have stuff going up and down. Here, it just slides along the table. On the Y-axis, honestly, I can never keep the Y and X straight, so I like that this has stickers because it helps keep me straight. And then our router moves across the gantry on the X-axis, and then the Z goes up and down. So that's how we can move in all 3 directions. So we can do 3D profiles or 2D profiles. If you're just doing 2D profiles, just cutting at a specified depth, then which was often called 2D plus, I want to say people call it, because then you're also adding that depth, but it's not changing depth. Then you're just moving off your X and Z, which is sort of your etch and sketch. You got 2 knobs, X and Z, going up and down or left and right. So that's the directions it moves, but how does it move? And I'm going to talk a little bit about options of different ways CNCs work. This one is using servo motors on a ball screw. I'm going to talk about the ball screw first. This is different from an ordinary screw. If we get in really close and you look, you'll notice that this is actually rounded off. That's because the nut that this runs on is a special nut that goes on this that actually has ball bearings. It's ball nut, I think it's called, that goes on the ball screw. And the reason for that is there's no backlash in this kind of system. So I'm going to try to explain backlash, because there are systems that use Acme screws instead of ball screws. The idea with backlash is if you've ever used a nut and bolt before, you notice that there's some slop in it. That translates into backlash whenever you're trying to use a thread for movement. Okay, and that backlash, that slop, is just this ability for me to wiggle this nut. That's important normally because it would be super hard if these were perfectly tight tolerances to ever thread a nut on a bolt, and they would have to all be manufactured perfectly. So they're manufactured with some tolerance, some slop, some free movement, just to make sure that you can always get nuts on bolts. Great for when you're using this as a regular nut and bolt. When you're using it to move things, not so great. So whether it's a CNC or a milling machine, a lathe, whatever. And the way that this slop translates into backlash is when we're going one direction to reverse direction, there is so much movement that happens before it starts pulling the other way, because there's that free range of movement. Now there are things called split nuts and ways to work around that. Just have to understand that backlash is a thing that exists, especially when you're dealing with Acme screws or other types of screws. Ball screws tend to not have that, so if you're looking at CNC machines, ball screws are often the way to go. If you do have backlash, that can be handled in your software, but either way, it's a thing that exists. If you're talking about CNCs, you need to understand that exists, and it's just the amount of movement that happens before you change direction when you change direction. So on this, let's say I can be, going one way, but I might have half a turn of slop before it actually starts going the other way if I change direction. Now, as long as my computer and motor know that, hey, when I start going the other direction, I'm not moving until after I do a half turn, so I always have to do that half turn before I can start calculating that I'm making movement, you're good to know. Just got to know that happens. The other common system for moving things is belts and pulleys. Issue with belts and pulleys and belt drives is belts can get loose and they can stretch and they're more likely to slip. And if a belt slips, then you can lose steps. We'll talk about that when we talk about motors more. And then rack and pinion is also common, which you normally see that on really big heavy-duty machines. If you're looking at home units, you're probably not going to see a rack and pinion system, but that's the same as the way steering is on car, which is a bar with a bunch of teeth sticking up and then a gear that kind of runs along those teeth. So the idea is that gear is driven by a motor, and as it turns that gear along that rack, it moves. Another thing to note is on this, because we're using this ball screw, the ball screw is just what provides the movement. It's not what keeps everything straight and in alignment. We have linear rails with linear bearings that mounted that help make sure that this stays trammed so the head doesn't end up, tipping out of axis this way or this way. Tramming is going to come up. It has to do with when your Z-axis, your spindle, is not perfectly perpendicular to the table. So if I'm perfectly straight up and down, everything's great. But if this is cocked at an angle one way or another, then with a big round bit, if I'm perfectly up and down, everything's great. But if that Z-axis is tipped, one end is going to be lower than the other. So whenever you do flattening passes, you're going to have tracks. If you see tracks on flattening passes where there's little bumps, that's a tramming issue. On larger industrial machines, that tends to all get worked out in the factory before shipping. My experience running this machine so far, zero tramming issues. On smaller, more residential machines, hobbyist machines, that can be an issue. If you're seeing that, you can normally work it out in your calibration. But anyway, this is providing the motion. My linear rails are keeping everything running track. These are the two on the Y-axis. On the Z-axis, I have two on each side. And then X-axis on my Y-axis down here, I have one on each side of the table. And then there's a ball screw that runs down the middle of the table connected to a motor. So that's what keeps the gantry running straight and not twisting. And that's all fine and dandy. We have movement, we have a way to keep that movement aligned and going straight. On my machine, for the movement, we have the ball screws. This could be an Acme screw, or it could be a belt, or it could be a pinion running on a rack. But something's got to make that move. That's a motor. On Penguin machines, we use servos. So these are heavy-duty servos. They could be stepper motors. Stepper motors are really common. Now this line is starting to get a little bit blurred with some of the brand new cutting-edge steppers. But generally, the big difference in rule of thumb between steppers and servos is a stepper motor is an open loop system, or really just a one-way system, where a servo is a closed loop or a continuous feedback system. With a stepper motor, the motor gets told to move by the controller, and then the controller has no idea if the motor was able to do that or not. So maybe there was too much resistance and the motor didn't move as much as it was supposed to. The controller doesn't know. Or maybe that belt slipped and the motion never translated. The controller doesn't know. And that's where we get into what's called missed steps, because a stepper is told to move in so many steps or micro steps. So it says, hey, blip this many times, which the controller knows is that many rotations, which based on the thread size or pulley size or teeth or whatever your drive is, it knows how much motion that translates into based on how many rotations it makes. But if it doesn't make the full amount of travel it's supposed to, then it's missed steps. A servo has that closed loop, that feedback. So the controller monitors this servo, they talk, there's an encoding system. So if this servo is told to move that screw 20 millimeters and it moves 19.5, it tells the controller, I moved 19.5, and the controller says, move that last half millimeter. And then he goes, okay, yeah, I did it. And now the machine still knows where the cutter head is. That gets really important. Is let's say that there is, a whole 10,000 movements that needs to happen. And on movement 50, your cutter head misses a step or is off by a fraction or even a fraction of a millimeter, a tiny amount. The problem is the 9,950 commands that come after that are all going to be off, because very early in that process, the point of reference that it was working from, because the way the encoding works is it says, okay, move X axis this far, move Y axis this far, move Z axis this far. Okay, you did that, now next step. Now move this direction this far, this direction that far, this direction that far. So it's all a relative movement, but that's assuming that everything happened like it was supposed to. So if something didn't happen the way it was supposed to, there's no correction in a stepper motor system, and then everything from that point is just not what you're hoping to get. That's a huge advantage to servos over steppers. So if you ever have an option, go with servo machines instead of a stepper machine, and it'll save you a lot of heartache and ruined projects. Okay, so we have a router that moves and cuts. It's driven by some sort of system. On this is ball screws, linear guides keep it aligned. The motor is providing the movement to that ball screw, but how does the motor know when to turn, how much to turn, which direction to turn, etc.? Well, that's where your drives come in. Stepper motors have drive, servo motors have drive, but there's special drives that are paired up to the motors. Because I have servos, these are servo drivers, and they're all labeled Z-axis, Y1, because on big machines you might actually have more than one Y motor. You might have two drive trains, drive systems, two motors on the Y-axis to make sure everything stays tracking in parallel, and an X. If you had a rotary system, then there would probably be another drive to turn that rotary if you have a 4-axis system. But this is what tells the motor where to turn. This is what does the translating. Well, how does the driver know what to tell the motor to do, when to go, which direction, how far, how long, how fast? That's where your controller comes in. So the controller is what lets us move the machine around, zero it, and all that stuff, which we'll talk about in a little bit. But more importantly, this machine, or this controller, I have a USB port, so I can plug this right into my computer. Then my computer will see it as a drive, and I can zip my code to it, or I can put it on a thumb drive, a little USB drive, stick it in the top, and then save that code to this. The code that tells a CNC to move is called G-code. There's different flavors of G-code depending on what machine you're using. This uses the generic G-code, which is called gerbil. Otherwise, depending on your machine, when you're in your software, you use what's called a post-processor. And the post-processor is what takes all the information you've told your software and then make sure that the G-code comes out of it is the flavor of G-code your machine likes, which might have differences like if there's a tool changer or certain settings on your stepper or servo motors, or how to set the spindle speed, if it's VFD driven, if the controller can control the speed of the spindle, which this one does. Those are all the different things that can be embedded in G-code, and then the post-processor knows what to add, what not to add, what commands it accepts. So the G-code goes in here, and then you tell it to run that G-code file you got from your computer. G-code goes from the controller to the drivers. Drivers then tell the motors how much to move. It's also tell the spindle to power on. Then from wherever your start point is, your 0, 0 for each of these axes, that's where it starts executing all those commands from. And then the cutter head in the spindle does all the cutting. All machines have a home on this machine, and it's normally front left with the spindle in the highest position. You can see I moved my machine so it's back over here. To make this go home, I can push the home button, then I can tell all of the axes to go home, and the machine is going to bring itself up to this corner and elevate the spindle all the way. Now, how does it know where that is? Well, for one, we have the servos, and the servos know how many rotations they make, and they talk back and forth with the computer, so they always know where they are. We also have these safeties. We have these little sensors. There's one here for the y-axis. There's one tucked away up here on the x-axis, and another one in here on the z-axis. And you see this is a sensor, and then there's a little metal bit hanging that when it comes over there, it knows it's home, and that's sort of a double check for the system. When you have a stepper motor system, you often have a physical limit switch, which is something that it bumps, and when it hits that switch, it actually makes a contact, sends a signal to the computer that says, hey, you hit me, you're all the way, don't go any farther, and that's what prevents your machine from running itself off the tracks. Although also some machines don't have that, don't have limit switches or anything, and you can literally tell it to try to run it, like it could be at the end of its travel, and if you tell that motor just keep turning, it's going to try to keep turning and tear itself apart. So always be aware of if you have limit switches or home, or if your machine knows where it is. But anyway, yeah, we're going to tell all axes to go home. It's going to bring itself here and go up. First thing it does is raise the z-axis. That helps make sure if there's any obstructions, it doesn't run into those with anything hanging down wherever the spindle is. Boom. Now the machine knows exactly where it is. This is home. Now Z is, or the origin, excuse me, not Z. The origin is a different thing. Like I was talking about, everything starts from wherever your start point is. Now, setting your origin is a very important thing whenever you run any programs, and this is one of those intimidating things where I think confusion comes in of like, how does the machine know to do what it's supposed to do, where it's supposed to do? It doesn't have eyeballs, so when I clamp this piece of wood right here, how does it know that I want it to cut my sign out of the top of this, and how tall it is and where to go? Well, that's where setting your origin comes on. Whenever you make the file that you're going to run this, tell it to cut whatever you want to cut here, you can pick an origin, which is normally going to be a corner or the center. And you pick that in the software. And then let's say on this, we're going to do the center. The other common place is the corner down here. We'd set it here. We'd draw our lines to find the center of this. This would be clamped on, of course. And now we're going to open up so we can see. Okay, now I'm not quite all the way down, but let's say I was flush and touching. This is all clamped. This is where my reference point, this is where I want the origin to be. So all the G code I talked about earlier, all the commands of, hey, move X this far, Y this far, Z this far, you know, then ditto, 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 are all referencing from that spot right there. And so long as everything's from that spot right there, my design is going to come out right. Well, then I hit XY0 and Z0. Now my machine knows that that is the origin. Whatever I'm about to tell it to do comes from this point in time and space. Really just space. There's no time here. Now the nice thing about servos and machines is I can also now hit home. It's going to raise the Z again. I'm just going to move over there. And this is the cool thing about the origin. I haven't moved this. We came to home. I can hit my origin button, say yes, I want to go to origin, and it's going to bring the machine right back to that 0. That origin is very important. That's how everything happens where you want it to happen. One thing is whenever you tell the origin though, it normally only goes to the XY. It doesn't bring the Z down. Most machines don't do that just in case anything has changed. It doesn't want to plunge that bit when it's not running into something and break the bit. But if I told it to execute a program again, then you know it'd fire up and go. And it even knows it because right here it says that the Z is plus 102.801. So it knows exactly how far it is from that origin point. And I can even bring it down, watch my numbers, and feather myself right into 0. Boom, and now my Z is back at 0, a little above the surface, because that's where I told it the origin was, even though ideally I'd want the origin to be the very top of the board, because that's what you'd build your model off of. So I think setting origin is a big thing to understand, and understanding how you take, you know, something software based and then translate it to something physical and make sure it happens where on the table you want it to. The other thing that took a while for me to understand how to translate is if, let's say I want to cut a sign out of this, some words, and that this is oversized, so then I'm going to have it cut perfect. Well, then I know my words are going to be straight and not like all cockeyed if I'm also cutting the entire sign out of this piece. But what if this is exactly what I want and I want to make sure those words are exactly straight on this? How do I do that? How do I know? Because that machine is, the computer's going to tell that machine to go one way, and if my axis and its axis are not aligned, then it's going to not be straight. Well, that's where your spoil boards and setups and everything come in. So before I get to any projects, next thing I'm going to do is make a spoil board. I'm going to get some MDF, which is going to go on this table. That serves a few purposes. A big one is then when I do through cuts and I go all the way through the material, I'm not tearing up all these pads. That bit would just be going into the MDF, which is sacrificial, can be removed and replaced. The other thing is what I can do with that MDF or anything I set here is make a program that the MDF is going to be slightly bigger than the cutting area and have that cut out exactly what its cutting area is and give me a lip that I can reference against. So when I butt things against that lip is the exact same in alignment with the axis, be it the x-axis or y-axis. Another thing you can do is have a series of holes drilled into it that you can put pegs into. Either way, that's part of the things of getting your machine set up is you'll build some sort of system on it, and there's all kinds of videos and great ideas, and some people have even put files out there that you can just have your machine run once you secure a spoil board to it to both flatten the spoil board so it's flat to your spindle, but also gives you reference points of some kind, so that way you can, bring in a finished board that you're ready to put a sign onto that you don't want to trim any material off of, set the origin to the center, or if you have a reference point, it's probably going to be the corner of your spoil board. You can have a place marked. That's the origin you always come back to. Set your stuff there, clamp it, and then have it run and have a finished piece. I hope that makes sense. It's really not that crazy. You just have to have a way of telling the machine where you're starting your code from, whether that's a corner, a center, which corner, and then you also need to make sure that this, whatever you want to be the left, right, back and forth is in line with the machine's left, right, back and forth. We just use fancy words like axis and origin and home and steps, but that's all it is. Where am I starting those instructions from, and making sure that my left and right and front and back are the same as the machine's left and right and front and back. And ultimately, that's how a CNC works. I'm not going to get into all the software side of things just because there's so many different software packages you can use. A really simple one to get started with is VCarve. Fusion 360 is a free one that you can use, but the CAM, the computer-aided machining, the part that actually takes your model and turns it into G-code, requires a little bit more knowledge, just a lot more settings, a little more convoluted. Inventables, which makes CNC, has a software package called Easel, which will spit out generic Gerbil GRBL code that this machine can run that Gerbil, and it has a free version of that software and a pro version of that software, which I've also heard is very easy to use, but there's lots of packages available. And the modeling and the G-code are actually two different aspects on the software side. When you're doing the modeling, that's CAD. That's your computer-aided drawing or designing, where you're making your model and like, this is the thing that I want a machine to cut. But then once you take that model and you start getting into the instructions this machine needs to know, like telling it what cutter head you're using, how fast that cutter head needs to spin, how fast you want that cutter head to move in this material, how deep that's going to be, what tools you're going to use, when to change those tools. All those instructions, which are called tool paths, that's your CAM side. And then for every line or whatever in your drawing, you have to build that tool path for, and that's a whole other thing, but that's where your G-code comes from. And those can be two different software packages. Sometimes you might be drawing in one program for your CAD and then take that design, move it into a CAM package to then export your G-code. We'll be doing some videos on that, but that'll be later on. This is more about just understanding how a CNC mechanically does what it does and why, and a few kind of tripping points on setting the Z-axis. So that can be a harder one. With the X and Y, one thing to note, especially if you have a V-bit which comes to a point and you have a mark on your wood, it's really easy to get that point right on the mark. But how do you know when you're touching the material or just shy of the material or rubbing material? One trick is to use a piece of paper and you bring it down till that paper just starts to feel resistance and set that as your 0. You can also use a touch probe. This is a touch probe. Lots of machines have touch probes, and the idea is, you can see this is on a cord that's connected, and there is some electrical charge on this spindle that carries to the cutter head, and when that cutter head touches this, it closes a circuit, and the controller knows, oh hey, that circuit was closed, that's 0. So on the controller there's a setting, I can come have this touch and it'll touch off. Actually, let's just do it. I set where I want it to. I want to cut this wood, and that's my origin. Well, here, let's make it more realistic. So that's the center. Say that's the center of the wood. I've got my puck under it. I'm going to 0 my X and Y. They're zeroed. Now I need to, the computer knows how thick this is, so when it touches that, closes the circuit, it's going to subtract the distance of my spacer and be good. So I just push the buttons that make it do it. It's going to come down. As soon as it touches and make contact, it's going to bounce off and 0 itself. Boom. That's it. That's how a touch probe works. And that's how a CNC works. I'll be going over some of this again in the project videos that are coming. So if you feel like I've earned it and you want to catch those, make sure you hit the subscribe button, hit the bell so YouTube tells you when those videos do come out. I just haven't had a chance to go get some MDF and get it set up and get my spoil board how I want to. And the projects I want to do would be through cuts, and I don't want to tear up all my pads. So we'll be doing that soon though. Anyway, I hope you learned something, were inspired, or at least entertained. And until next time, make time to make something.